Hello, welcome viewers. So we are going to discuss about the discrete mathematics. It is the basic discrete mathematics. So what are the main points in this basic discrete mathematics? They are say sets, relations, functions, combinatorics, partitions, and etc. Rather, it is in basic discrete mathematics. It is the base for the higher and the advanced discrete mathematics. Now, let's start with the topic. First of all, say some basic things. That is sets. What is a set? We call a set. It is a well-defined collection of the objects. Well-defined means they are in the definite order. As we say over counting 1, 2, 3, 4, because see 4 comes after 3 and after 4 it will come 5. Never we will write 5 after 5, 7. They are in order. Then we say it is the set of the natural numbers. We can represent it in the two forms, that is roster form, or we say it is tabular form. And second, it is set builder form. Set builder. It is a well-defined collection of the objects, right? How we say roster form. Say we take a set A is equal to, that is 1, 2, 3, 4, 5 and so on. It is a set of the natural numbers. And say another set, say A is equal to A, E, I, O, U. It is the set of the vowels. If we write them in this form, it is the roster or the tabular form. We deal with this form mostly in this topic. We can consider some or more examples. Say A is equal to 2, 4, 6, 8, 10 and so on. It is the set of all the even natural numbers. We can represent this form also in the set builder form. First of all, we see all the elements or members or objects, they are in the definite pattern. This is called the set. If we want to write them into the set builder form, that's for this. We write, say, A. Generalize the natural number. We say X is such that X belongs to N. Who is N? N is the set of the natural numbers. Similarly, for this we can represent like this A with consider any element, say X, and we write X is vowel. And in this A, X is such that X is even natural number. That is the representation of this set in the two forms, roster form and the set builder form. That's when where the problem arises. Let us say here we take a set, say A is equal to X is such that X square minus 5X plus 6 is equal to 0. We are given this set. Then how to convert it into the roster form? Simple, it is a quadratic equation and we can solve it. X square minus 5X plus 6 is equal to 0. That is X square minus 3X minus 2X plus 6 is equal to 0. X minus 3 minus 2 common, X minus 3 is equal to 0. X minus 3 into x minus 2 is equal to 0. It is a simple middle term splitting of a quadratic equation. So in roster form, we write this set A is equal to, we got two values 2 and 3. That is the representation of a set. Now, secondly, we see these objects or the elements or the members, they can be counted, they cannot be counted, such that in this case 1, 2, 3, 4, 5 and so on. Such sets are called infinite. Such sets are called infinite. And the sets in which we can count the members, like this, it is finite set. It is finite set. Then we can represent a finite set. Let us see this, like this. Here A is set of the vowels A, E, I, O, U. Here we can write N, A is equal to 5. N stands for the cardinal number. It stands for cardinal number. Or we can say there are the 5 members in the set. So only the finite sets we can write their cardinal numbers. After that, we see that is a null set. What is a null set? We denote it by letter phi. It is phi, P-H-I, phi. Null set is the set which contains no element. It contains no element. Or we say it is an empty set. Null set, we say it is empty set or void set. It does not have any member. Then what's about the singleton set? Singleton. Singleton set means a set which contains only one element. Let us say A, C is equal to 5. It is singleton element. Now what's about this? A is equal to 0. It is also a singleton set because 0 is also an element. Here the cardinal number both the sets is 1. Cardinal number both the sets is 1. That is singleton set. Now we are interested in finding after set what is a subset. For that, let us try to understand with a simple diagram. Say it is the main circle, or we say it is the set, say B, and it is the small circle inside the larger circle. We call, say it is A. According to geometry, we say that A is contained in B, or we can say radius of A is less than the radius of B. But in our discrete mathematics, how we represent it? Like this. We consider a member, say X. Here we see X belongs to B. X here we represent belongs to B, but X do not belongs to A. X belongs to B, but X do not belong to A. It means we can say that A is not the part of B. A is not the part of B. If we take some other example, like saying here it is the set B and it is the set A. Now we write this element X. Here, no. X is present in A. It means X is also present in B. X is present in A. It means X is also present in B. If it is so, then we call A is subset of B. It is the sign for subset. It is the sign of subset. Or we can write in this way, X is such that X belongs to A such that X belongs to B. Then we say A is subset of B, or we say B is the superset of the A. Here are some considerations regarding the subsets like this. What we say, first of all, every set is subset of itself. Then number two, null set means phi is subset of every set, Third, it's very important, total number of subsets in a set that is equal to 2 raised to the power n. These are the three main rules or conditions or the considerations associated with the subset. They are very important. From this, we will proceed our topic further. Let's see, what is the power of a set? Power of a set, we represent it by PA. Here, let us take an example. Say A is equal to 1, 2 and 3. Power of set means it is the set of all the subsets. It is the set of all the subsets of a set. That is called the power of a set. Let us try to write the subset for this set. Here we write 1, 2, 3, 1, 2, 2, 3, 1, 3. 1, 2, 3, 4, 5, 6. They are 6 elements. But what the rule says, how much members must be there? 2 raised to the power 3, that is equal to 8. Then, what is the problem here? Where are the 2 members? The members are present here. First, every set is subset of itself. So we write 1, 2, 3. Second, 5. It is the subset of every set. We can write in this way or in bracket, that's the same thing. Now we count 1, 2, 3, 4, 5, 6, 7, 8. These sets are complete. Every time we consider these 2 steps or these 2 sets in every set as a subset. So we can say it is the power of the set A. What is the power of the set A? That is equal to 8. Power means how many subsets a set can generate. How many sets a set can generate. It is the set of all the subsets of a set plus these 2 particular sets always. That is set itself at the null set or the void set. This is called the subset. No, we will discuss about the properties or the applications of the set theory. That is, first of all, we see union of 2 sets. Union of 2 sets. Because it is a discrete mathematics. In discrete mathematics, all these things, they do not follow the rules of our arithmetic, plus, minus, multiplication. All the rules, they are in the different manner which exist here. That we have to discuss how that arithmetics we discuss into the discrete mathematics. First of all, union of two sets. It will be better we consider, say some example, A is equal to 2, 4, 5, 7, 8 and B is equal to 1, 2, 3, 4, 5. Then A union B. A union B. It is a sign for union. It is a sign for union. A union B means combine the members of the both sets. Combine the members of the both sets by keeping in mind that no member should repeat itself. No member should repeat itself. Just if we start combining, we say 2 is also present here, 2 is also present here, so 1 and 2. We write 2 only once. Then 3, again 4 is present here, 4 is also, we write it only for once. 4, 5, 7 and 8. It is the union of two sets. Union means we combine the members of both the sets by keeping in mind particular case no member should repeat itself if its repetition is present. If it is not present, then there is no problem. We can mix them. Here, in the set builder form, how we write it? A union B is equal to this. X, read it, such that X is such that X belongs to A or X belongs to B. In our general language, it means union stands for or. Union means or. It means the element will belong to A or B, not to both. Set 2 is also here, 2 is also here, but here it is only single 2. So 2, it either belong to this or belong to this. Now, along with this definition, some important work is how to draw the Venn diagram. So, Venn is the name of the mathematicians who gave the solution of these problems diagrammatically like this. We call them Venn diagrams. For union, we can draw a Venn diagram in this way. Let us consider these are the two sets A and B. What we do in the union, we combine all the members. We consider all the members like this. Like this. We share this. It is a Venn diagram for the union of two sets. It is the roster form or the tabular form, and it is the set builder form. Only we have to remember in our general language, union means or. Similarly, now we discuss the intersection of the two sets. Intersection. Thus, we keep the same problems, same example here. A is equal to this and B is equal to this. Then, what does mean A intersection B? Intersection we denoted by this. Simple. It is the set of all elements. See, in both sets, which elements are common? Here 2, here 2. And we write 2. See, 1, here is 1 not present, 3 not present, 4 is present. Then see, 5 is also present. It means we count or we delete those elements which are common in both, If we want to write it in the set builder form, we write it in this way. X is such that X belongs to A and X belongs to B. It means in our general language, intersection means and. Intersection means and. It will help us to solve some problems if we keep them in mind. Now, how to draw its Venn diagram? Again, we take a set of A and B, A and B. Now, what we have deleted the common elements from the both the sets. It means this portion which is under shade, it is the A intersection B. Or we can say, if we want to write these elements, we will write here 2, 4 and 5 in this portion. That is why X belongs to A and B. This 2 belongs to A, also belongs to B. 4 belongs to A, also to B. That is the intersection of the two sets. These sets may be in any form, and that is the Venn diagram for this. No. What happens if there is, say, no element is common? We say A is equal to 1, 2, 3 and B is equal to 4 and 6. Very simple. We say A intersection B. There is no common element. There is no common element. And we denote it by phi. Phi means null set. Such sets, if it is the case, such sets are called the disjoint sets. Disjoint sets. It means disjoint sets are those when their intersection does not contain any member. That is the void set or the null set. Next. Next application of the property of the sets, we say difference of two sets. Difference of two sets. It is not same as in the arithmetics. That is a subtraction. It is not a subtraction. What does it mean in our discrete mathematics? Let us first of all understand it by an example, then we will try to write them in the standard forms. Let us see here an example, say 2, 3, 4, 7, 8 and B is equal to 1, 3, 5, 6, 9. Here we have two sets. What does A minus B means? A minus B. In generally, if we discuss A minus B means those elements of A which are not in B. We look for those elements of A which are not in B. Let us consider, we start from A because it is A minus B. 2 is present here, but 2 is not present here. So we write 2. 3 is present here, 3 is also present here. We can't consider. 4 is present here, 4 is not present here. 4. Then 7 present here, not present here. Then 8 is present here, but not present here. It is A minus B. It means those elements of A which are not in B. Similarly, we can write B minus A. For B minus A, we start with B. We start with B how? Those elements of B which are not in A. Let us say 1 present here, not present here. 3 present here, also present here. 5 present here, not present here. 6 present here, not present here. 9 present here, not present here. It is B minus A. It means in discrete mathematics, A minus B is not equal to B minus A, because it is not the arithmetical subtraction. A minus B means those elements of A which are not into B. We can write it into the set filter form, right, like this. A minus B is equal to X such that X is any arbitrary element such that X belongs to A, X belongs to A, comma, X do not belong to B. And what is B minus A? We reverse the condition. That is, X is such that X belongs to B, comma, X does not belongs to A. And what's about the Venn diagram? For A minus B, we write in this way, like this. Here, there are the two sets, say A and B. What is A minus B? Those elements of A which are not in B. That's the case which we shaded. It is A minus B. If we have to find B minus A, then we write in this way. Again, two sets, A and B, A, B, then we shade the B. It is B minus A. Both are different. Both are different. We compile the result, this and this, for a very important concept. Let us see. That is the symmetric difference. That what is the symmetric difference? Symmetric difference. We denote it by capital delta. It is a capital delta. Here, delta means symmetric difference, that is equal to A minus B union B minus A. Nothing new. All the three concepts we know. We can find out A minus B, we can find out B minus A. Then we take the union, that will give the symmetric difference of the given two sets. Let us see with in example, say let A is equal to 2, 3, 4, 6, 7 and B is equal to 1, 2, 5, 6, 8 and 9. Here are the two sets we considered. So we find A minus B. A minus B means those elements of A which are not in B. 2 present here, 3 present here, not present here, 3. After that 4, 6, 7, not present. It is 3, 4, 7. Then we consider B minus A. Now we start counting with B. Those elements of B which are not in A. Say it is 1, 2, here 5, 1, 5, 6 is present, here present, then 8 and 9. Then what is the symmetric difference? Symmetric difference means A minus B union B minus A. That is equal to, see, if we unite them, 3, 4, 7, 1, 5, 8 and 9. That is the symmetric difference. But there is some particularity in this result that we see them carefully. Here the elements are 3, 4, 7, 1, 5, 8, 9. There is no element common. There is no element common. It means their intersection is empty. Their intersection is Empty means always empty for symmetric difference. That is, how do we draw the Venn diagram for this? That is, first set, second set, that is, we say it is A and B, then A, and we leave the intersecting portion. It is the diagram for symmetric difference delta. See, here intersection is empty. It means intersection is empty. See, here there is no element in the intersection. So we can write A minus B in the set builder form like this. X is such that X do not belong to A intersection B. These are the main three important definitions for the applications or the properties of the sets: union, intersection, and the symmetric difference. Now let us consider another concept, say complement of a set. For complement, to find the complement of a set, we need a main set to which we find the complement of the given set. It means the main set. A set, we know, can have 2 raised to the power n subsets, so many sets. If every set is contained in a set, that set is the universal set. That set is the universal set. Say, we consider a universal set, say, that is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. Then A is equal to 3, 5, 7, 8, 9. Here is the A. Then what do we mean by complement? We denote complement by like this: A, C, or A dash. Those elements in the universal set, those elements are in the universal set which are not in A, Let us cross them. Here 3 present, we cross with 3. 5, we cross with 5. Here 7, we cross it with 7. Here 8, we cross it with 8. 9, here it is 9. Then the remaining elements are 1, 2, 4 and 6. Then we say it is the complement of this set. A dash is the complement of this. If we take the complement of this, again, that's complement of the complement. Again we get elements 3, 5, 7, 8 and 9. It has become a universal law. What? First of all, we say complement of the complement of a set is again the set A. That's the complement. Means for complement, we need a main set which can contain many sets, so that we can find the complement of the main set with respect to that main set. So how it's Venn diagram like this. Here is the set A. The remaining one outside circle, it is U, and here it is A complement. It is a Venn diagram complement of a set. In complement of the set, very important result is that they are the De Morgan's law. It is the universal set will be obeyed. What is the De Morgan's law? Morgan's law. They are important in a concept of the complement of the set. You see, A union B complement is equal to complement intersection B complement. Second, A intersection B complement is equal to A complement B complement. In particular, what do we say? When we take the complement, the union converts into the intersection, and intersection into the union with the separate complements. Here we see the function in the example and also in the theoretic form. Let us example say A is equal to 2, 3, 5, 7, 8 and B is equal to 1, 3, 6, 9. Here are the given sets. We want to verify the De Morgan's law. By De Morgan's law, we take first A union B. A union B complement is equal to A complement intersection B complement. And take left hand side is A union B complement. Find first of all A union B. And we take reverse set for this 1, 2, 3, 4, 5, 6, 7, 8 and 9. A union B means to combine the elements, it is 1, 2, 3, 5, 6, 7, 8 and 9. It is A union B. Now we take the complement of A union B. Complement of A union B means with respect to this, we say crossing the 1, present 2, present 3, present 5, present 6, present 7, 8, present. Only there is 4. That is, we write A union B complement equal to 4. Then we take right hand side. We take right hand side that A complement B complement. Or we take A complement that is A complement with respect to this. That is equal to 1, 2. We can mark 2, 3, 5, 7 and 8. The elements are 1, 4, 6 and 1, 4, 6 and 9. Then what about B complement? B complement again we identify 1, 2, 3, 6 and 9. Then we have 4, 5, 7, 8. No. A complement into B complement. Okay. That is equal to, therefore left side is equal to right. So in the we can solve an example which we studied difference, union, intersection in the numerical box. Let us see one more example. Just if let A is equal to 1, 2, 3, 4 and 5 and B equal to 4, 5, 6, 7, 8. Prove that A minus B is equal to A intersection. Then what we studied, still those definitions or the results we can apply in such problems. Let's take left side. For left side, first of all we solve this problem A minus B. That is both elements of A which are not in B. It is 1, 2, 3, 4 here. 1, 2, 3. No. A minus B. Both elements of A which are not A minus B. 1 present, 2 present, 3 present. Remaining are 4 and 5. Then right hand side that is equal to A intersection B. Here A intersection B. What are the common elements? 4 and 5. 4 and 5. So the result is proved. Such type of the numericals, we can solve any kind of numericals using intersection, union, symmetric difference we can find, and also like such problems in this way. No. Further, let us discuss about some important Venn diagrams. Let us see how to create or how to draw the Venn diagrams when there are more than two sets. Let us see simple Venn diagram for, draw the Venn diagram for A union B intersection C. It's very simple. We consider here 3 circles. That's it. Start solving the problem from the brackets. It is B intersection C. It's B. It is C. We start with bracket. B intersection C. Here it is B intersection See? No. This bracket has union with A. It means A will cross in both the circles. Union means we combine all the elements of A with the elements of B intersection C, like this. Then it is the Venn diagram for A union B intersection C, and your result will lie in this shaded portion. If we get the final result, those elements will come into this section. This is dark. Again, let us see some more example. Say A union B intersection C. That is equal to, again we have three sets. Draw. Start with the bracket. It's A union B. We draw A, B, and we take its union. Like this, it is the union. We cover the whole portion on the both sets. It means all the elements are combined, keeping in view no element should repeat. It is A union B. But this bracket, whole bracket, has intersection with C. So OC will intersect with both the circles. And what does mean intersection? Common portion. That is a common portion. If we give them different direction, that is this portion, it is if we dark it, then it is our requirement and it is the Venn diagram for this one. In this way, we can draw the different Venn diagrams for the different sets, particularly when they are three. First, always start with the bracket. Always start with the bracket. From inner, then outside. Inner, then outside. Let's see. Say note that two sets are equal. A is equal to B. If we say A is subset of B and B is subset of A. It is the sign for the subset. If A is subset of B and B is subset of A, then we say A is equal to B. Now we are going to use it in the next topic. In the De Morgan's law, thus first, before this we discussed the verification by taking an example. There was verify the De Morgan's law. We can take any example. But sometimes the problem is, in spite of verifying, prove the De Morgan's law. How to prove the De Morgan's law? That is, say, first prove, we can say A union B complement is equal to A complement intersection B complement. If it is to be verified, we can take any example. But if you have to prove it, we will have to prove it theoretically. In this way, that's we are going to do. We know two sets are equal if A is subset of B and B is subset of A. Let us start from the left hand side. Left hand side, let us start, that is, we say any element X belongs to A union B complement. What does it imply? This implies X do not belong to A union B. If complement is removed, complement means yes converts into no, no converts into yes. This implies union. Union means, in general language we say or. It means X do not belong to A or X do not belong to B. We are expanding the result every step into the other step by using the basic rules. Now here we take the complement like this. If X does not belong to A, it means X belongs to A complement, X belongs to A complement. X does not belong to B means X belongs to B complement, and or. What's about the or? Complement contains into and. Or converts into and after complement. This implies X belongs to, we know and means A complement intersection B complement. We started from this side and left on this side. What does it imply? This implies A union B complement is subset of A complement intersection B complement. We consider it the first part. Similarly, now we start from the right side. From right side, and we will finish it on the left. We started first right, left, then finished at right. Now we will start from the right and finish at the left. We will consider some other elements, say Y. Y belongs to A complement intersection B complement. It means Y belongs to, this implies Y belongs to A complement and Y belongs to B complement, because intersection means and. If Y belongs to A complement, it means Y do not belong to A and Y do not belong to B. And Y do not belong to B. If we take complement, it means Y belongs to A or Y belongs to B. In complement, and changes to or. This implies Y belongs to A union B. Y belongs to A union B. This implies Y do not belong to A union B complement. Therefore, we have proved that A complement intersection B complement is subset of A union B complement. Then from 1 and 2, if we combine them, we say the result A union B complement is equal to A complement intersection B complement. That is the proof of the De Morgan's law. In the same manner, we can prove the other results. We see, now we will discuss some application of the set theory which we studied into the practical problems. Say, for that we see some results. Then N A union B is equal to NA plus NB minus NA intersection B. Then N for three sets A union B union C, that is equal to NA plus NB plus NC minus NA intersection B minus NB intersection C minus NA intersection C plus NA intersection B intersection C. It is for the three sets. First result, second and third one. NA minus B. It means belongs to A, do not belongs to B. That is equal to NA minus NA intersection B. These are the few results which we use into the application of this set theory which we studied. Let us take an example, very simple. That is, in a group of, we write, say, in a group of 1000 students, 750 can speak Hindi, 400 can speak Bengali, find the number of people, a number of students or number of persons, same thing, students who can speak only Hindi, who can speak only Hindi. We see there are total 1000 students. Here 750 can speak Hindi and 400 can speak Bengali. The total has 1150. That increased from 1000. It means there are many students present who can speak both Hindi and Bengali. It means this 1000, it is the union of all the students, and A union B is equal to 1000, or we can say among the 1000 students, every student can speak at least one language, and there are many students who can speak also both languages. And A union B is equal to this. Let us consider, let's say A is equal to number of students who speak Hindi, and B is equal to number of students who speak Bengali. It means their cardinal number NA, they are 750, and NB, who can speak Bengali, they are 400. Our requirement is only Hindi. Only Hindi means N, only Hindi. It means those students of A which are not in B. It means N A minus B. That is equal to NA minus NA intersection B. That is, here the problem is we don't have the intersection. Intersection means it is not given the number of students who can speak both the languages. It means Hindi and Bengali. That can be found with the separate formula. N A union B is equal to NA plus NB minus NA intersection B. So NA union B, it is 1000. NA, it is 750 plus NB 400 minus NA intersection B. From this we can find out that is NA intersection B, that is equal to 1150 minus 1000, that is equal to 150. If we put this value in 1, then put in 1, we can find N only Hindi, and those students who can speak only Hindi, that is equal to NA, that is 750 minus NA intersection B 150, that is equal to 600. It means 600 students are here which can speak only Hindi. Similarly, we can find out only Bengali. If we subtract from 4150, that is 250. That is 250 who can speak only Bengali. In this way, we can apply the results to the practical problems or the numerical problems by using the given results. Now we see what is the Cartesian product. Cartesian product of two sets. It is not the product, arithmetic product or the multiplication. It is the Cartesian product. Cartesian, the name of the mathematician. Then how we find out? Say, let us consider two sets. Say A is equal to 1, 2, 3 and B is equal to say 2, 3 and 5. Then Cartesian product we denote by A cross B. That is equal to, start with 1, it is 1, 2, or we can draw a simple table. Say we have to find A cross B. We write A here 1, 2, 3 and B here 2, 3, 5. Then Cartesian product. This with this we write 1, 2, 1, 3, 1, 5, 2, 2, 2, 3, 2, 5, 3, 2, 3, 3 and 3. So we write it 1, 2, 1, 3, 1, 5, 2, 2, 2, 3, 2, 5, 3, 2, 3, 3, 3, 5. That is the Cartesian product of the two sets. We can find out it depending upon the number of the sets. It is not necessary the cardinal number is same. The cardinal number must be maybe the different also. In the same manner we can find out the Cartesian product. Sometimes the problem arises like this. See, if we are given the set A, and we have to find A cross A Cartesian product A, that's very simple. That is two-dimensional geometry. But what happens if we extend result to this? A Cartesian product A, or you can say a cube. How to find it? Now our problem has converted into the three-dimensional geometry. Like this, we find out it in this way. We draw the three axes in this way, where we write the elements like this: 1, 2, 3, say 1, 2, 3, 1, 2, 3. Now, we start writing this. Start with this one. Start with this one, then this one. Fix them. We will move 1, 1 and 1. It is 1, 1, 1. That is, we start with 1, 1, 1. It is the first member. No? 1, 1, 2. 1, 1, 2. Then 1, 1, 3. 1, 1, 3. Now change the second axis to 2. First axis is again fixed, and we repeat the same procedure with 1, 2, 1, 1, 1, 2, 2, 1, 2, 3. Then we change the second axis to 3. It is 1, 3, 1, 1, 3, 2, 1, 3, 3. Again, start with, we change the first member to the second member of the first axis, and again we start with here. That is 2, 1, 1, 2, 1, 2, 2, 1, 3. Then this side 2, 2, 1, 2, 2, 2, 2, 2, 3. Then with 3, it is 2, 3, 1, 2, 3, 2, 2, 3, 3. Now we change the axis again. First axis, x-axis to the 3. Again we start with the same point. It is 3, 1, 1, 3, 1, 2, 3, 1, 3. Then with 2. It is 3, 2, 1, 3, 2, 2, 3, 2, 3. And in last, it is 3 with 3. It is 3, 3, 1, 3, 3, 2, 3, 3, 3. That's seems to be typical. It's a three-dimensional. It is a triple product of the set. A set. We can find out in this way by drawing the three axes. From the set theory, here we have discussed about the Cartesian product. In the Cartesian product, what we do, we consider each and every member which comes into the Cartesian product. No, we define a relation. Relation means it is also, we can say, a Cartesian product of the two sets, but under certain condition, how the two sets are related. How the two sets are related. See, let us take an example. Let us take an example, say A is equal to 1, 2, 4 and B is equal to 2, 3, 5. Ordinal number may be same or may not be same. Let us find the Cartesian product. Say we write A cross B, 1, 2, 4, it is 2, 3, 5. But no, we are not interested in finding the Cartesian product. We are interested in generating a relation. Relation means some arithmetical and algebraic relations. Let us consider a relation here. It is greater than. It is greater than. We say we will consider only those members of the Cartesian product who will follow this rule. See, 1, 2. 1 is not greater than 2. We don't consider. 1, 3. We don't consider. 1, 5. We don't consider. 2. We don't consider. 2, 3. We don't consider. 2, 5. Don't consider because 2 is less than 5. No. 4, 2. Yes. 4 is greater than 2. 4, 3. Yes. 4 is greater than 3. 4, 5. Again we say no. Here we consider the elements 4, 2 and 4, 3. Now it is not a Cartesian product. Rather it is derived by the Cartesian product, but it has followed some rule. That is the greater than. Then we say it is a relation. It is a relation. We can write a relation like this: x comma y such that x is greater than y. Here is the relation. For x is the first member, y is the last member. Or we can consider another example in it. Say it is less than, greater, less than or equal to 2. Less than or equal to 2. We have considered also 2. Again we write the relation here. 1, 2 we can consider because 1 is less than 2. 1, 3 we can consider. 1, 5 can be considered. 2, 2 can be considered because equal to sign exists. 2, 3 yes exists. 2, 5 also exists. 4, 2 can't consider because 4 is greater than 2. 4, 3 cannot be considered. 4, 5 yes it can be considered. So we can write the relation 1, 2, 1, 3, 1, 5, 2, 2, 2, 3, 2, 5, 4, 5. So we write the relation in such a way: R is x comma y such that x is less than or equal to y. So there can be many relations. It can be minus, it can be divisible, it can be the modulus. So these are the relations. Relations means those members in the Cartesian product which are related to each other under the given condition. Now, see, these first members, they are called the domain. It is called the domain of a relation, and this member is called the range of the relation. We write in this way: domain of the relation R. Here in this domain is 1, 2 and 4. No element should be repeated. Then what is the range? R. It means range of the relation. Elements 2, 3, 5, 2, 3, 5. It is the range of the relation. Simply we can find out it. And sometimes we can also find the inverse of a relation, R inverse. What we do in the R inverse, we interchange the range and the domain. Say in this example, we can write it in this way: 2, 1, 3, 1, 5, 1, 2, 2, 2, 3, 2, 5, 4, 3, 1, 5, 1, we have to reverse the elements, 5, 1, 2, 2, 3, 2, 5, 2, and 5. It is the inverse of a relation. These are some properties associated with the relation. So first of all, it is very necessary to understand what is a relation. Relation means how the elements are related to each other. Here we see each of the first element is lesser than the other ordinate member. Let us consider more examples. Let us say A is the set 2, 3, 5, 2, 3, 5, 8, and B is the set 1, 3, 4, and 6. Define a relation R is such that x comma y is such that modulus of x minus y is greater than or equal to. That's the problem. Now we have to derive the relation according to the given condition. That's the same procedure we have. A, 2, 3, 5, 8. Then B, 1, 3, 4, and 6. What is our requirement? Modulus of x minus y. Modulus means always positive. 2 minus 1, 1 cannot be considered. 2 minus 3, 1 cannot be considered. 2 minus 4, it is equal to 2. We can consider it. 2, 4. Then 2, 6. 2 minus 6 is equal to 4 and 4 is greater than or equal to 2. 3, 1 can be considered because 3 minus 1 equal to 2. 3 minus 3 cannot be considered. 3 minus 4 cannot be considered. 3 minus 6, no. 5 minus 1. 3 minus 6, we can consider it. 3 minus 6, 3. And 3 is greater than or equal to 2. 5 minus 1 can be considered 4. 5 minus 3, it is 2. 5, 4 cannot be considered. 5, 6, no. 8, 1 can be considered. 8, 3 can be considered. 8, 4 can be considered. 8, 6 can be considered. That is the relation. We can derive it. 2, 4, 2, 6, 3, 1, 3, 6, 5, 1, 5, 3, 8, 1, 8, 3, 8, 4, 8, 6. So we can find its domain, range, and the inverse of this relation. Let us see one more example in this. Say, here is the set, say A is equal to 1, 2, 3, 4, 5, 6. Define a relation x, y such that y is equal to x plus 1. How to find the relation? See, we have relation y is equal to x plus 1. We write the relation r is equal to, we take value of x, that is 1. If x is 1, y is 2. If x is 2, y is 3. X is 3, y is 4. It's 4, 5. X is 5, it is 6. X is 6, it is 7. It is a relation. No. Here is some problem. Problem is this. 7. Because 7 does not belong to the family, does not belong to the set. So we cannot consider this member. So the remaining members, they are the relation according to this given function or the relation. That's it. About the relations too much. You can ask any question about what we discussed today in this regard. And it's okay. Good day.